All right, welcome back, everybody. So this is just the second video on separation of variables. We're going to make it pretty quick and just go through two more examples. We encountered the Laplace's equation in the last video, and now we're just going to move on to the heat and wave equations by separation of variables. So I'll get in this example, a one space and one time dimensional heat equation. So from that sense, you can really think about that Laplacian really just as partial x squared. So that is that Laplacian there, since we're in one space and one time dimension. And then we have ourselves a temporal boundary condition, which you can also call an initial condition. This is the initial distribution of heat. And then we also have boundary conditions, spatial boundary conditions. Both sides are equal to 0. This says that on the left and right, we have a temperature fixed at 0. Okay, so just imagine a rod, and it has an initial temperature distribution given as x, pi minus x. If this is 0 and pi over here, the distribution will look something like that. So it'll be hotter in the center, and then it's equal to temperature of 0 on both sides. So we've achieved the physically impossible absolute 0 on the left and the right with a rod. But that's our initial distribution of heat, and we're going to try to use separation of variables to see how this heat would evolve over time. And you can imagine just like perfect ice cubes sitting on both sides here, so temperature fixed at 0. Okay, so what are we going to do if we're doing separation of variables? Separation of variables solves that for us. It doesn't solve the boundaries for us until we get to step 8. And if you forgot the steps, the separation of variables, maybe pause the video, go back to the previous video, and I go through them there. But I do have the steps labeled here. And in the first step, we just make the ansatz, which says that our solution phi is going to be a product of a solution a function just in time and a function just in space. So phi of t times psi of x. Now what we do with that is we grab that product of functions. This is in step 2. We grab the product of functions and actually plug it in here. When we do that, we're just going to be taking one derivative in time, which on there is just going to show up as phi prime, and we're going to take two derivatives in space, which on here is going to show up as psi double prime. So we'll end up with basically the equation that phi prime of t psi of x equals phi of t psi double prime of x. This is what the ansatz gets us in step 2. Step 3, you'll recall, well, really at the end of step 2, but then moving to step 3. So at the end of step 2, we need to solve this set of equations for one variable to, let's just say, the left-hand side. Of course, you can decide whichever side you want, but let's solve for only one variable onto the left-hand side to make the choice of t. If we're going to solve for everything in terms of t on the left-hand side, what do I have to do? I have to divide by that phi, I have to divide by that psi, and so you get phi prime of t over phi of t is psi double prime of x divided by psi of x. Okay, so that's really what we do at the end of step 2. There it is. And then moving to step 3, we actually set up differential equations from this and solve them. So what's so important is that the left-hand side here, right, and the right-hand side depend on distinct variables, and hence both are equal to a constant. And I'll put this in parentheses, the same constant. So we choose some constant. Once again, I'm going to give it the name lambda squared instead of just lambda. This is just a benefit of, whatever power you put on lambda, it's useful to grab the top order of the differential equation to be that power in lambda. But it really doesn't matter, right? Because we could always reverse the powers later. A constant squared is still a constant. That's what I should say. So we're going to give it the name lambda squared. And so both sides of this equation are equal to lambda squared. And that gives us two independent ODEs. Basically anytime we're solving PDEs, what we actually try to do is solve a finite number of ODEs, sometimes an infinite number of ODEs. But either way, we're trying to convert a PDE into ODEs. Separation of variables is one way to do that, if it works. And so what we have here is two ODEs that we can solve independently. And in fact, if we simply rearrange this, I've got a slight typo here, it should be squared there. If we simply rearrange this, we do have phi prime as lambda squared phi, which is probably one of the easiest ODEs to solve. This is first order linear. And the solution is given by a constant, which may depend on lambda, times e to the lambda squared t. Similarly for psi, moving to step 5, we can rearrange our equation in psi to a second order linear ODE. Solution to a second order linear ODE, you can do this in lots of ways. I mean, I would often say you probably want to do this with the characteristic equation. Check out section 1.4 of this book if you're curious how to solve those still. But I would use the characteristic equation. You find your roots, you have lambda and negative lambda are your roots of your characteristic equation, and so those are the powers of the exponentials, and then you have some undetermined coefficients that probably depend on lambda that are going to sit out front. So what do we have up here is we have a solution in phi, a solution in psi, and if we go all the way back up to the separation of variables ansatz, the ansatz is that the true solution to the problem is a product of the solution phi and the solution psi. So we're going to jump back down here, take our solution phi and our solution psi, and we're going to multiply them. So when we multiply phi and psi together, we get our true solution. Parentheses dependent on lambda. And in fact, this should be interpreted as dependent on all possible lambdas. That's kind of the true point of separation of variables, is really it's dependent on all possible lambda. This is how we're going to meet boundary conditions, by considering all possible lambda and in fact the principle of superposition. So you do have your solution dependent on a specific lambda, but by the principle of superposition, because this is a linear PDE, we can actually take an infinite sum, or perhaps integral, over all possible lambda. Now, this term possible is important. So I say possible lambda. The boundary conditions tell us which lambda are possible. This is kind of another important point about separation of variables. Yeah, they can solve the PDE for us, but once we get to the superposition part and we decide, what is this collection of possible lambdas we can sum over, we have to be careful that at each stage along the way, right, that at each lambda we choose, this actually solves boundaries. So we need to choose a specific collection of lambda for which that is actually going to solve the boundaries for us. So when we do that, we have to evaluate phi at the boundaries. Let's scroll all the way back up to what phi looked like on the boundary. That's this line right here. And so there are two conditions about phi on the boundary. The first is that it's equal to 0 when x is 0, and the second is that it's equal to 0 when x is pi. And so we have two situations that can help us determine which possible lambda we can use. So the first is that, so the first boundary condition is that phi evaluated at 0 is equal to 0. But of course we know what phi looks like, so we know how to evaluate it at 0. To evaluate at 0, we just plug 0 in for x, and we get this sum of d1s and d2s. Well, the only possible way that this is going to be satisfied for all times, right, assuming that this term is not identically equal to 0, we're going to assume that that's not 0, because otherwise we would never be evolving over time. So let's assume that that's not 0. The only way that this is equal to 0 is if d1 plus d2 is equal to 0. So I have that condition on my d's, or equivalently that d1 minus d2, or d1 is equal to minus d2. The second boundary condition, remember the first one was at 0, the second one occurs when we plug in pi for x, and we can do that up here, pi for x in our solution for phi. Plugging in pi for x, we end up with once again the same sort of linear combination where this is not actually going to be 0, so that's not 0, so we're going to ask ourselves that this linear combination be 0 for all lambdas. And that's going to tell me that d1 lambda e to the lambda pi plus d2 lambda e to the lambda negative lambda pi is 0. Or if I rearrange that, d1 lambda e to the lambda pi is negative d2 lambda e to the negative lambda pi. So what do I have for my boundary conditions? My boundary conditions independently give me this relationship between d1 lambdas and this relationship between d1 and d2 lambdas. So what can I do is I can use this first equation, plug it into the second equation, and then if this negative d2 is just d1 by the first equation. What do I have is a d1 there. The d1's cancel from both sides, and I see that this shows up. E to the lambda pi is e to the minus lambda pi. Well, that can only be true if e to the 2 lambda pi is equal to 1. Now, what do we know about Euler's formula? Let's jump back to Euler's formula. That, e to the, let's say e to, I'll just write it out as it is. E to the 2 lambda pi, this is going to be cosine of minus I pi 2 lambda plus I sine minus I pi 2 lambda. This needs to be equal to 1. And sine can never take on imaginary values, so I need that sine term to always be equal to 0, and I need this cosine term to always be equal to 1. You can certainly solve that just by using your unit circle, and you find out that lambda has to be in the imaginary integers. Okay, so just I times any integer. So I1, I2, I3, I4, negative I, negative 2I, and so on. So that's the only possible choices of lambda to meet these boundary conditions, right? This is what I mean when we jump back up here to say where capital lambda is some set of possible lambda values which satisfy the boundary conditions. We just use the boundary conditions to show us that the only possible choices for these lambdas are these. So plug everything into the boundary conditions. You're going to find out the possible choices for lambda. So what we do at this point is we use those choices for lambda in our solution here, and we make, lambda I n and negative I n, and we make this n in the integers, and then this will just be I n. This will be, what is I n squared? That's just negative n squared. But more importantly, what's going on here is we can rewrite that in terms of sine, right? Euler's formula says this is sine. Sine nx. So looking into Euler's formula, I mean, you'd technically have to absorb some constants into d1 and d2, but more or less you can rewrite that as sine of nx. So that's what I've done here. I've really absorbed all of my constants into just this single constant, c star. You can absorb a lot of different constants into the c1 term out front to just call it c star. There's really only one function of n sitting around still, or one function of lambda sitting around still. And so this is what the function actually has to look like, the solution actually has to look like. And what are we starting to notice, actually? This e to the minus n squared t. This is precisely the solution to the heat equation via Fourier methods. So not really a huge surprise there, because that's this object. That's the Fourier multiplier version of e to the t delta, right? E to the t Laplacian. The Fourier multiplier of that was e to the minus n squared t, if you jump back a couple sections in the book. So not really a surprise that we've just recovered our Fourier method solution, but now we do have to finish one last piece, because right now we satisfy boundary conditions, but not initial conditions. So there's one initial condition we do still have to satisfy. Let's jump up there really quick. My initial condition is right here. I have to meet x times pi minus x when t is 0. So we'll scroll down to where we were, and I'm going to evaluate this function at t being 0. So that makes the exponential 1, and we just end up with it's called a Fourier sine series. So the Fourier sine series is sitting there, and you can calculate the coefficients just like you would from the regular Fourier series. I'll just mention coefficients of series like this are always the integral over your bounds, which in this case is 0 to pi. You always have to normalize that integral, 1 over pi. And then all you do is you grab this term, and you integrate. So we're going to do sine nx, x pi minus x dx. So this is going to be c star of n. And if we go ahead and compute that, we find out that c star is exactly that term. That's going to be when n is not equal to 0. Right. When n is equal to 0, what should it be? Well, it's not too bad, because sine at 0 is 0, and so actually the n equals 0 case kind of takes care of itself. Because sine of 0 is 0, so our integral at sine of 0 is also 0. Okay, so what does that mean? Our solution is, well, we just grab that, what we've calculated for C star, and we plug it right in for C star. There it is. And then we recover our exponential term and our sine term, and we have our infinite series. And there isn't probably no closed form. Version of this, but we can plot approximations. So as always, a lot of these Fourier series solutions don't necessarily have a closed form, but we can definitely plot a solution, and this is evolving over time. So as t moves forward in time, you move to the right and then down, and you can kind of see if we fixed both endpoints at a fixed temperature of 0, then certainly the heat should diffuse to the endpoints. But since we have kind of, think about it as an infinite amount of ice on both ends, then it just tries to melt that little bit of ice, and it doesn't do anything to it because there's an infinite amount of ice there. And so the heat just diffuses to the boundaries and would eventually go down to 0. So the total amount of heat 0 over that equilibrium in this case. So that's how we can use separation of variables. And really, this was really just the same sort of heat equation that our Fourier methods could solve, but we saw the separation of variables version of that. And then let's do the same for the final equation of the Holy Trinity, which is the wave equation. And we are going to skip, I'll mention this up here, we are going to skip step 8 in separation of variables for this case. And there's a few reasons. Number one is that I set it up so that this is arbitrary. We have an arbitrary initial condition, initial wave height, or wave shape, I should say. And then this is the initial wave velocity. They're both left arbitrary here. But more importantly, you could technically still produce a version of a solution with arbitrary ones of these. You would just have like inverse Fourier transforms of these functions. But the real reason I don't go through step 8 here is that we're going to do this in 2 spatial dimensions and 1 time dimension. I mean, basically always there's only 1 time dimension, but we're going to do 2 spatial dimensions. And when you do the separation of variables for a number of spatial dimensions greater than 1, things can get pretty ugly, and we're going to find that out here. But I wanted to give at least one example of a higher spatial dimension version of separation of variables, because this is where you have a non-trivial step in, I think this is step 5. So there's like a non-trivial step 5 when your spatial dimension is greater than 1. And so I want to give at least one example of that, but that makes step 8 really, really tricky. So it's another reason why I don't really love the separation of variables compared to other methods, because you're in higher, as spatial dimensions increase in separation of variables, your life gets really hard. Like, it's already hard in one spatial dimension, but as you get higher and higher, your life gets harder and harder. And other methods, sure, they get harder, but not in the same way. They kind of treat all spatial dimensions equally, where separation of variables really, because it's an iterative process where you're working your way through the total number of dimensions, you have to put a lot more work in when you have higher number of dimensions than 2 total dimensions, or 1 spatial and 1 temporal dimension. Anyway, so we're going to skip step 8, but we're going to go through kind of steps 1 through 7 to see how this works in 2 spatial dimensions instead of 1. So we have the wave equation here. This kind of looks the same as what we've been dealing with this whole chapter. So we have the wave equation there. We've got our, as I mentioned already, the initial wave shape and the initial wave velocity, which means we don't really have a boundary condition in space. We only have kind of this like boundary condition in time, or your initial condition. So in space, we're working over all of R2. This would make this setup really, really well for our Fourier methods. Whatever, let's go through separation of variables instead and see what we get. So making the separation of variables ansatz, we're just going to assume our function is a product of one function, a function only of time, a function only of space, and a function only of space. So here's my 2 spatial variables, x and y, my temporal variable t. And let's recall that's the Greek letter xi, spelled xi if you transliterate its name, but that's a Greek letter xi, and so I'll be referring to it as xi for this example. And then the way we actually use separation of variables, we grab that ansatz and we plug it in here for phi on both sides. So when we plug it in for phi on both sides, 2 time derivatives is going to go beep beep, 2 time derivatives there, and then the Laplacian is going to be 2 spatial derivatives in x plus 2 spatial derivatives in y. So there's my 2 derivatives in time, 2 derivatives in x plus 2 derivatives in y. That's what step 2 gives us. And then at the end, we choose one variable that we want to isolate. In this case, I've decided to choose x as the variable I'm going to isolate to the left-hand side. And so I'm looking at those 3 cases of psi, and I want to isolate them to the left-hand side. So what do I do? I want to keep the primes on the top, so really there's a lot of rearranging going on. So really I subtract this entire term to the left-hand side. I move this entire term to the right-hand side, and then I can combine some things together, and then I'm really dividing by these terms as well. And what happens then is I get psi double prime x over psi of x isolated on the left-hand side. And interestingly enough, the other terms kind of isolate themselves too, even though there are two total terms here, they are definitely isolated as only terms in t minus only terms in y. So it's really nice. Everything kind of works out there, even though these aren't across from each other, at least across from an equal sign. But I do have this term with only x's on the far left, and then kind of the whole point of separation of variables says, hey, if these are equal and dependent on different variables, then they both must be equal to the same constant. Okay, we're going to choose, once again, a lambda squared because these are second order problems. But we're going to need more than one lambda here, and that's because we have a total of 3 variables. You always need one fewer lambdas than the number of variables you have, so 3 minus 1 is 2. And we need a total of 2 lambdas, but we're just going to start with lambda 1. I'm splitting this up. Both sides both have to be equal to lambda 1 squared. So I've taken the entire left side, said that's lambda 1 squared, the entire right side, that's also lambda 1 squared. What I can do now is this is an ODE. I mean, technically that's like a version of an ODE too, but we wouldn't know how to solve it in its current form, so we're going to forget about that for now. I can solve this as an ODE, and when I do solve it as an ODE, I end up with, it's just second order linear, just like before, I end up with my exponentials to a plus and minus lambda 1 with some undetermined coefficients. So that's a pretty easy ODE to solve. Now, moving to step 5, this is the non-trivial version of step 5, finally. So what do we have left over? We can't solve it currently as an ODE because we both have we have t's and y's sitting around. So what do we do is we've reduced ourselves away from the variable x, and we just have variables t's and y's, and we can isolate all terms of variable y to left-hand side. And when we isolate all terms from the variable y to the left-hand side, what we end up with is phi double prime t over phi t minus lambda 1 squared. But at this stage, we actually have the same case that we had before. We have a function of y equal to a function of t, and hence both are equal to the same new constant. Right, so there's some new constant here, lambda 2, or lambda 2 squared. I'm going to be using that both sides of this equality must be equal to, because everything on the left is a function of y and everything on the right is a function of t. So everything on the left has to be equal to a constant. Call it lambda 2 squared. Everything on the right has to be equal to a constant. But this is important, that everything on the right includes our first constant, lambda 1, and then we set it equal to lambda 2 squared. So there is a relationship between lambda 1 and lambda 2 built in here, and we have to keep it around. So that relationship between lambda 1 and lambda 2 has to be built in and kept around, but it does just show up as lambda 2 in the second case for whatever variable I solve for second, which in this case was y. But there will be a relationship. The very last, there will always be a relationship between all of your lambdas, no matter how many dimensions we're in at least one of the equations. So what do we have here is we have an ODE in the variable y. We actually have an ODE in the variable t as well. So we can solve both of those ODEs. If we solve the ODE in the variable y, it's really not too bad. It's the same as before, just a second order linear ODE with some undetermined coefficients of d1 and d2, which perhaps depend on lambda 2. This ODE in phi maybe is a little trickier. So let's rearrange to a second order linear ODE as, well, what am I going to do? I'm going to isolate phi double prime to the left-hand side. So phi double prime of t equals, I'm going to bring this minus lambda to the right, and then I'm going to multiply by phi. So I have lambda 1 squared plus lambda 2 squared phi of t. So if you do the characteristic polynomial here, you'd find out that it's the plus and minus square root of that term that's going to be in your exponentials. So then phi is actually going to be some function of lambda 1 and lambda 2, and then e to the square root. So this e is just an arbitrary coefficient. This e is, the second e is Euler's constant. E to the square root lambda 1 squared plus lambda 2 squared, t plus some other undetermined coefficient, and then e to the minus square root lambda 1 squared plus lambda 2 squared t. So that's going to be the solution in t, which is what I have written down here. So the E1 and the E2, these are just because I started with C for my coefficients and then D's and then E, so I went C, D, E. Okay, so we found psi, we found xi, and we found phi. So we can find our overall solution dependent on this choice of lambdas, lambda 1 and lambda 2, as the product of all three of them. So this was psi here, this was xi here, and this is phi down here. So we just take the product of all three, because that is our separation of variables ansatz. So you take the product of all three, and that's our overall solution. Of course, that solution depends on lambda 1 and lambda 2, and of course the relationship lambda 1 squared plus lambda 2 squared. But we can use the principle of superposition to say, hey, I can actually sum this over infinitely many lambdas. And in this case, I chose the integral. Why did I choose the integral? I chose the integral instead of sum because the boundary of the PDE was infinite. So we should start getting used to this with the Fourier series and Fourier transform, that an infinite boundary problem in space utilizes the Fourier transform, or the integral version of the Fourier transform, and the finite boundary version of PDEs always uses the Fourier series instead. So you just have to, basically use the following assumption, is that finite boundary implies a series, in lambda, and an infinite boundary implies an integral in lambda, if you're using separation of variables. Otherwise, your Fourier methods will kind of tell you what to do anyway. But because my boundary, I'll just verify this for you really quick at the beginning, because my boundary, here you go, that's R2. It's everything, infinitely large space. Because that's infinite, we're going to use integrals instead of series. But the principle of superposition, so we're just going to integrate over all of lambda 1s and lambda 2s here. And we can simplify kind of this giant product of functions I have here. If I FOIL this all out and combine terms together, then I can kind of come up with, there's a function that depends on lambda 1, there's a function that depends on lambda 2, for exactly two terms. What terms are they? They're the terms with the positive root here and terms with the negative root here in front of t. So you kind of have to be a little bit clever and kind of force the Fourier transform to show up here. But what happens when you do force the Fourier transform to show up here, right? What did I do to get it to show up? I kind of replaced lambda 1 with I lambda 1, and I replaced lambda 2 with I lambda 2, and so on. That's how I could force the Fourier transform to show up. Once I do force it to show up, however, what do we actually see here? What is this power? And in particular, what is this term? That term is exactly e to the t plus or minus delta to the 1/2, the square root of the Laplacian, which is precisely what my Fourier methods gave. Okay, so really, we went through a whole bunch of extra work to just find the Fourier method solutions again with this e to the plus or minus t delta to the 1/2. But now I guess you see a different perspective on coming up to these same solutions. Now we haven't gone to step 8, right? Step 8 would be to find these. And it's not so trivial how you would find those functions, but if you did go through the huge amount of work, you would just recover the Fourier method solution. So I really don't like this method as much as the Fourier method solution, but to each their own. This is definitely one perspective on solving some of these PDEs, and at least you've seen it now. And in fact, I have this remark as well, that the separation of variables methods were the original Fourier methods. So we're older and wiser as a civilization to know that the Fourier methods are kind of just better than separation of variables. In, I'd say 99% of situations, there are some situations where separation of variables will be to your advantage, but you'll just have to come across those organically. But in the 1800s, when Fourier was developing everything he did, he actually started with separation of variables. I think the mathematical community knew about separation of variables first. They didn't really know about the Fourier method, and so he got into this point where he had superposition of infinitely many functions which solved a PDE, and he was trying to meet initial and boundary conditions with these superpositions. And that's actually how he originally developed his series, was that he wanted to solve the heat equation, and he had already solved it with separation of variables. He just didn't know how to solve the boundary conditions for it. And so he developed his Fourier series to solve the boundary conditions of the heat equation. And then other mathematicians came along after him and said, wait a minute, we can actually extend these results to all sorts of crazy problems which are harder than the heat equation. So Fourier had really good ideas, and then they just kind of blossomed into our modern perspective on these ideas and our modern perspective on solving PDEs. But anyway, there's separations of variables for you. I hope you liked it enough, even though I'm not a huge fan. We'll practice these a lot in class. I'll see you then. Bye.